divides b to the power of n, then a divides b. The other direction is trivial. This direction is obvious, but the proof isn't trivial. So we will do it. Last time I proved up to this point. If GCD of xy is 1, then the greatest common divisor of x to the power of anything, y to the power of n, equals 1. I proved this in last time. So on top of this, I will prove this fact. First of all, we will consider GCD of two numbers, a and b. And we assume that this GCD is g, right? So let the number GCD be g. Then, because of this fact, we can rewrite a and b. A and b can be rewritten because we have a divisor, right? So g divides a, meaning a is equal to g times some number x, and then b is g times some number y. Then, with this thing, we can write GCD of a to the power of n and b to the power of n. Because a to the power of n divides b to the power of n, we have GCD of a to the power of n, and then this divides the other one, so a to the power of n times some number, say t, right? Do you follow me? Because a to the power of n divides b. b is equal to a to the power of n times some integer, or we are handling integers. So, because of this fact, it is a to the power of n. Any questions? Because a to the power of n divides both numbers, and the maximum number that we can find is a to the power of n. Any questions? So a to the power of n divides both numbers, and then the maximum number that we can find is a to the power of n. So GCD of this thing is a to the power of n. Now let's write the GCD in different pattern. GCD of a to the power of n and b to the power of n can be rewritten using this fact. A to the power of n is gx to the power of n, and then b to the power of n is gy to the power of n, and then it is GCD of g to the power of n, x to the power of n, g to the power of n, y to the power of n, and we can factor out the common factor, g to the power of n, then GCD of x to the power of n, and then y to the power of n. Do you follow me? We can extract the common factor out in GCD calculation. Then, because of this GCD fact, here we can get GCD of xy equals what? Because g is the greatest common divisor, we have GCD of xy equal to what? GCD of xy should be equal to GCD of AB is g, right? But if we divide by g and get xy, then GCD of xy should be equal to what? 1. Do you follow me or not? Right? If there is more common factor, then we can extract bigger number, right? Because we extracted the biggest number possible, GCD of xy is 1. But because of the fact that we proved last time, if GCD of xy is 1, then x to the power of n, y to the power of 1. So, because of the region, it is g to the power of n times 1. If you have any questions or doubts about any step here, you can ask any step. Then, what can you get? We can get this conclusion. We can get this conclusion. AN equals GN and means A is equal to G. It's not GCD anymore. It's just straightforward algebra, right? A to the power n is equal to the G to the power n. A and G are all positive, so A equals G. Thus, I will go to the right side. Thus, GCD of A, B equals G equals A, right? GCD of AB is G and G equals A. It means A divides both numbers, right? So A divides B and we are done, right? So I completely showed you the proof. If you have a question about any step, you can ask me. Last time we proved this part. As you can see, even the simple statement is not trivial to prove. And last time I showed you how to prove this thing using some A, B, GCD of A, B, comma, Y equals 1, right? I used these things before. Any questions? So it is a little bit long. But in any case, we completely proved this case. Then today, we will begin to study about new chapter. And new chapter is way tougher than the previous one because it involves multiplication. So I will be very slow in this chapter. But before going further, if you didn't receive the exam sheets, you may approach and take it. So, tell me your name, then I will give it to you.
Peter.
Just a moment. So this chapter is the real application and theory combined. So this is the high-tech chapter. The theory covered here is embedded in your cell phone and or encryption. And I will make this very simple. High-tech doesn't mean difficult. High-tech means it is very sophisticated in theory, but in reality could not be very difficult. So let's check it. It is 0 o'clock, 3 o'clock here, 6 o'clock here, 9 o'clock here, and then in between, right? 1, 2, right? So you assume that you have a clock having 0 o'clock through 11 o'clock, right? So 0 o'clock through 11 o'clock. Then assume that someone tells you 5 hours later from 11 o'clock, then what is it? 5 hours later from 11 o'clock. 5 hours later, then it means 4 o'clock, right? So in this sense, we can create this kind of statement of 5 hours later from 11 o'clock gave us 4 o'clock. You can play on these things. 6 o'clock plus 7 hours, then 1 o'clock, right? All these are very familiar things. And in reality, these are used not with 12 hours. We are using 12-hour system, or sometimes 24-hour system, but we are using like our system, right? This is the similarity and the difference. We are handling a similar thing with these many hour system, right? So we have these many hours instead of just 12 hours. Do you follow me? Essentially, what we are handling is the same. But when we are handling just 12-hour system, then 11 o'clock plus 5 hours is 4 o'clock, right? 6 o'clock plus 7 hours is 1 o'clock. But in encryption or in your cell phones, we use bigger hour system, right? So we have like these many hours embedded. Then it's not that trivial. Assume that I say this, oh, plus this hour. Then can you easily calculate it? For instance, this plus this hour, or bigger thing, like 10 to the 50th power plus this thing. Then can you check what time it is? It's not like 12-hour system, even though idea and theory are all the same, right? 12 o'clock system theory and this theory are the same. But in reality, we can easily calculate, for instance, 5 hours later or 7 hours later. But we cannot easily calculate, for instance, 1,001 hours later. We cannot easily calculate. Not because of the theoretical difficulty, but because of the size, right? Sheer size. So do you follow me? Essentially, what we will handle in this chapter is like this clock system with not just 12 hours, very many hours, like these many hours, right? So please check and ask. So essentially, what we will do is this. We will develop system indicating 1 o'clock. 1 o'clock is 1 o'clock. 13 is also 1 o'clock, but they are not equal, right? 1 and 13 are not equal, so I will attach one more bar. And 25 o'clock, right? All of these are the same, right? And you can imagine, right? 49 o'clock or something in between, right? Or after. So these are the things, they are called congruent, right? So 1, 13, 25, 49 are different as numbers. But in this, our system or clock, we regard all these the same time, right? So in our congruence, we regard this the same time. So generally, I will define it. Let's define this. A is congruent to B, right? A is congruent to B. Assume that we are using 12 o'clock system, then we don't have to indicate, but assume that we are using different hour system. So modulo n. N could be 12, right? Or 24-hour system. So we use this thing, and then I will write down the way to read these things. We say this. A is congruent to B modulo n. So you will read this way. Just the reading, just the definition. When, if A minus B, or B minus, it doesn't matter, right? A minus B is divided by n. This is it. Very simple. A minus B is divided by n. or b minus a is divided by n. The same thing, right? Just minus sign difference. It is also not usual mathematical expression. It is just in concept. How can we rewrite this concept in equation form, inequality form? How can you do it? A minus b is divided by n. It can be written in this way, inequality form. Inequality form, a minus b is equal to what? N times some number, right? Then we say that a is congruent to b modulo n. Just the definition. So in this sense, I can write it this way. Oh, 1 o'clock is congruent to 13 o'clock, and this is congruent to 49 o'clock, and it's congruent to 1 o'clock modulo 12. Do you follow me? Why? Because if we subtract 1 minus 13, then negative 12, right? Negative 12 is divided by 12. Or 49 minus 13, that is 36. 36 is divided by 12. Or 12,000, 1 o'clock minus 1. Then 12,000, right? 12,000 is divided by 12. So all these are congruent. Any questions? Then, why do we use this thing in modern cryptography or in your device such as cell phone? Assume that you are transmitting some signal. So you are sending, for instance, your account information. You are sending your account information using your cell phone. If you directly send, then someone else may have a snipping tool and then read your signal. Do you follow me? Then the other party can intercept and then use this account number to do other activities, right? So we don't send this way. So instead of sending this, assume that we are using, for instance, 5-digit modulus, then we break this up into 5 digits, right? 2 5 digits. And then after doing it, we use, for instance, something like this. Something like this system, and then scramble it. So we scramble this number using mod calculation and create some number. For the first part and for the second part, like this, right? So when we really send from our cell phone, instead of the original signal, this encrypted signal goes. So assume that you have a snipping tool and then capture this number and type in, you cannot log on, right? You cannot access the account. Then the other party uses decrypting code using the same modulus and then decrypt this number to the original number and then access the account. So these are used in almost all modern devices, especially requiring some security. So when you access bank account or other things, they use these things. Then the difficulty of cracking depends on the size. Assume that we use, for instance, a 100-bit number, then it is 100-bit encryption. Assume that we have 1,000, we use 1,000 bit, then it is 1,000-bit encryption, and it's very tough to crack, and I will tell you the reason later. Very difficult to crack it if we use bigger number. Small number we may be able to crack. Any questions? In any case, all these things come from the very simple idea, clock calculation, right? Clock of not just 12 hours, clock of millions or trillions of hours, right? Then I will show you how we can speed up the calculation in real circuit design or programming. Generally, big numbers are not easy to handle, but under this circumstance, it's very fast to calculate any power, addition, subtraction, power, using this congruence. Without congruence is very tough, but with congruence is very trivial. I will show you. But if you have a question, ask me. I'm not covering the real technique other than the definition. But if you have a question or a feeling or something, ask. Then let's do it. First of all, I will just state many things, and only when the difficult proof is required, then I will prove. But if it's not, then I will just skip, and later, when you have enough time, I will return back and prove a few easy cases. But mostly, when it is easy or trivial, I will just state the theorem. It's called, this is theorem 4.1, and then the idea is this. If A is congruent to B, mod n, modulo n, right? A is congruent to B, mod n, then A and B have the same remainder, same non-negative. It could be zero, so I don't want to say positive, so I want to say the same non-negative remainder. Assume that you divide 13 o'clock by 12. Then, after removing 12, you will get 1, right? So it's exactly the one that I mentioned. Then the next theorem is the collection of simple, small facts. A is congruent to A. Do you agree with me or not? Obvious, right? And if A is congruent to B, right? If the first condition didn't have if, the second thing has if, right? If A is congruent to B, then B is congruent to A. Obvious, right? 1 o'clock and 13 o'clock, 13 o'clock and 1 o'clock are the same, right? The third fact, if A is congruent to B and B is congruent to C, then A is congruent to C. The next thing, if A is congruent to B and then C is congruent to D, then we can, like equalities, we can add these two things, we can subtract these two things, we can multiply these two things, right? Like congruence, like equalities that we handled before. So I will write down all the cases. A plus B, A plus C is congruent to B plus D, and A, C is congruent to BD, right? Any questions? What about the other way? We can use property number 2, because C is congruent to D, D is congruent to C. So we can say A plus minus D is congruent to B plus minus C, right? Do you get it? You can just switch. This isn't limited to just left side and the left side, right side and right. We can switch it, right, by using property 2. But we don't write it because it's obvious. But if you want me, then I want me to, then I can do it. The next thing, if A is congruent to B, then A plus C is congruent to B plus C. Obvious, right? Why? By first property, C is congruent to C, right? C is congruent to C. Then we can just add. And then same thing, AC is congruent to BC, right? Obvious. Do you follow me? Because of this thing with CC, just we can apply property 4. Property 6. if A is congruent to B, then A to the power of K, B to the power of K are congruent for any integer K. How can you get it? From number 4. We write AB, right? We write AB, then AA, BB. And then we can continue, right? AA, BB, and then continue these steps to get this. So all these are written, and I will prove these kind of things later. When you have enough time, I will prove harder things or harder techniques first, and then later, if you have enough time, we can return back. Then, all kinds of things I'll add. As I mentioned before, these are high-tech techniques. So we want to use these things with actual calculation. The real key is powering like this to the power of this kind of powering. We want to use this tool in this kind of powering. Then suddenly it's not very simple, right? So in usual calculation, this will be extremely tough if you don't take number theory course, and if you are asked to implement this thing, then you multiply this how many times? Million times, right? You need to multiply these things billion times, and then later divide the number by this, and then find the remainder. Your algorithm may not run because of the overflow problem. But today I will show you how people implement these things in small devices like cell phones. So let's handle simple things first. Assume that you are handling mod 9. Mod 9 and 2 to the power of 7. So you want to find the remainder or smallest positive number representing 2 to the power of 7. Then let's do it. 2 to the power of 7. To handle this thing, 2 to the power of 3 might be good, because 2 to the power of 3 is what? 8. 8 is congruent to negative 1 mod 9. Is it true or not? With mod 9, 8 is congruent to minus 1. Then, if we square it, by the sixth property that I mentioned, if we square it, then it will be the same, right? Do you follow me? If we square it, then the left side is multiplying this thing twice, right? Squaring. And the right side is multiplying negative 1 twice and 1. Meaning, 2 to the power of 6 is congruent. 2 to the power of 6 is congruent to 1. 2 to the power of 6 is congruent to 1. Then 2 to the power of 7, to handle 2 to the power of 7, all we need to do is attaching one more 2, right? One more 2. Then now we can multiply the left side to get 2 to the power of 7. And we can multiply the right side to get 2. Then mod 9. So this kind of technique is the major thing that we want to consider. So suddenly, this section becomes very technical. In the first two chapters, we studied about proofs, but now it becomes technical. So let's really verify this thing using MATLAB. You can access MATLAB on any computer in this building, right? So on any computer in this building, and just go there and then type in 2 to the power of 7, 2 to the power of 7. Then you get this kind of number. If you divide this by 9, then the quotient is 1 and then about 6, right? 1 and 4, right? 14, right? 14 is the quotient. Then the remainder is 2. Do you follow me? Or MATLAB has a built-in function handling it, mod 128 or 2 to the power of 7 modulus 9, right? Do you follow me? mod 2 to the power of 7 mod 9. Just a moment. I will let the people look at this result. So you can see these kind of things, right? Any questions? So we are developing this kind of technique here. So by these kind of techniques, we can reduce the amount of time per calculation. And pick any big prime number. For instance, it may not have a built-in function. Do you know how to generate any prime in MATLAB? Then just use some known prime, 101. I will ask the question first. Can you guess what may happen? Pick any number less than 100. Pick any number. 82. Did you say 8? 82. 82. And then I will use Can you guess it? So let's use MATLAB to handle the case. 82 was chosen by you, right? I do not know whether overflow problem may happen here or not. It is not right. This is not. MATLAB cannot handle it.
Is it 1?
Yes, right. This is 1, but MATLAB couldn't handle it. Then you may wonder what may happen if we use different number, 41, 1, 32, 1. How do I know these things? Because I studied section. I will show you the section that we will cover very soon. It is, just a moment, as soon as I find it, I will. So it is page 88. Page 88. Page 88, top. You can see the top of page 88. Do you see it? It is called Fermat's theorem. So we are not interested in just brute force calculation. I will show you some brute force calculation, but we are more interested in theories like this. Do you follow me? Without theories, MATLAB could not handle this thing, right? MATLAB could not handle this thing. Do you see it? MATLAB couldn't handle it because it tried very hard, but it has some truncation problem that creates the wrong result. So we will cover these kind of things. In any case, I will tell you about the actual brute force type calculation. It's not very brute because we will use smart idea to handle the problem, but not as smart as theorems like this. Not as smart as theorems like this. In any case, we will learn both sides. Brute force calculation, or a little bit smaller calculation, but later we will cover theories. These theories are the reason that your cell phone could handle these kind of calculations. In any case, if you don't have a question, I will continue. If you have a question, ask me. There are very nice properties for mod 3, mod 9, mod 11. So let's explore. With mod 9, 10 is congruent to a very simple number. What is it? 1. Right? So assume that you are handling 1, 2, 3. In general, 1 to 3 is 123. But in mod calculation with mod 9, it is 100 is equivalent to what? Any power is equivalent to 1, right? 100 is equivalent to 1. 2 is equivalent to 2, right? 3 is congruent to 3, right? So it is 6. Do you follow me or not? With mod calculation, 10 is congruent to 1. 10 times 10 is congruent to 1, right? 10 times 10 times 10 is also congruent to 1. Then you can write these things like just one-digit number, and let's verify. Always verifying gives you confidence. Mod 1, 2, 3, 9, right? 6. How do I know it? Because I studied small theorems like these, right? Small theorems like these. So 10 is congruent to 1, then 10 times 10 is congruent to 1 by property number 4, right? Property item 4. So property item 4 is extremely important, right? We have 10, 1, 10, 1, right? 10, 1, 10, 1, then 10 squared is congruent to 1 squared or 1. 10 squared multiplied by 10, 10 cubed is congruent to 1, and so on. So we have this property. Then using the property, we can say this kind of thing. Then what about mod 11? Let's go to the right side. With mod 11, ten is congruent to what? Simple number? Negative 1, right? 10 is congruent to negative 1. So any odd power is congruent to negative 1. Any even power is congruent to what? 1, right? Minus 1 times minus 1 is 1. So it alternates, right? So assume that you have 1 to 3. Then any even position, right, is just this, and then odd position is a zeroth power, right? First power, second power, right? 10 to the power of 2, right? 10 to the power of 2, 10 to the power of 1, 10 to the power of 0. So zeroth position, 3, negative position, negative 2, and then 1. And then congruent 2. In fact, this is equal. So let's check it. Always check the result. Mod 1 to 3, modulus is 11, then 2. How did I know it? Because I used the simple theorems, right? Simple items in the theorem, and then derive this. So by now it doesn't look very bad, like handling clock. But about 2 accumulations later, if someone didn't attend 2 classes in a row, and then comes on third time, the person will have no idea, absolutely no idea. Really. So I showed you a few cases. Any other questions? Then let's continue and then cover a few interesting cases the text handles. Example 4.2, 2 to the power of 20 minus 1 mod 41. In fact, when I took a number theory course for the first time in my life, I was asked some problem like this. I should have used some powerful theorems, but my brain was completely blank. And I tried to rely on my hand calculator. My professor was very nice. He allowed me to use calculator. So I multiplied the 2 and then 2 and so on. I used up all my time on solving just one problem, but that problem was also wrong because I mistyped something. So I got very bad grade. So this course is not about brute force. It's about some nice ideas. Nice idea. So first of all, this kind of thing is not difficult to handle, right? This kind of thing is not difficult to handle. So we ignore. We will focus on this part. So let's multiply 2, then 2 next time, 4, 8, right? Still no clue, right? And then 16, still no clue. One more time, 32. In other words, 2 to the power of 1 is not very interesting. 2 to the power of 2 is not. 3 is not. 4 is not. 5 is close to 41. How close? About 9 away, right? About 9 away. Do you get it? So we are getting some number close to 0. Then, suddenly, here, we are not handling 2 to the power of some number anymore. We are handling 9. If we multiply 9, then 81. Do you get it? If you multiply 9 twice, then 81. Then 81 is congruent to what? 81 divided by 41. 41 multiplied by 2 is what? 82, right? So 81 is congruent to what? Negative 1, right? Do you get it? Then once we get 1, we should use this case over and over again. Why? No matter how many times we multiply, it will not expand, right? It will just stay in this limit. So the next time I will do is, what I will do is this thing. Do you get it? So this is the brute force, but a little bit smaller direction. I didn't use any special theorem that I will gradually cover in 2 consecutive sections. But without any special thing, with just careful investigation, you can find numbers that is closer to 0. So take a look. Take a look. 2 to the power 1, 2, 3, 4, 5. Up to 5, we didn't get any interesting result, right? But about 5, we got minus 9, close to 0, right? And then 9 squared is 81. 81 is close to 0. And then we squared this thing to get 1. Then let's find the relation. We squared it, right? We squared it. So we should square the left side. What is it? 2 to the power what? 10. So 2 to the power of 10 is congruent to 81. And then it's congruent to negative 1. Then now we squared it. So what is it? 2 to the power what? 20, right? So 2 to the power of 20 is congruent to 1. Then we arrive at the goal, right? So it is congruent to, this is congruent to 1 minus 1, and then it's essentially 0. So this is the result. So with just brute force calculation, with smarter idea, we could handle it without really calculating all the powers. Do you get it? So when you want to use brute force calculation, try to find the number which could go to 0, right? Or could be close to 0, right? So that kind of number should be found. Any questions? So it is 41-hour clock, right? 41-hour clock system. And then in 41-hour clock system, like 32 o'clock is minus 9 o'clock. And 2 to the power of 10 o'clock is minus 1 o'clock. 2 to the power of 20 o'clock is 1 o'clock. Then the next thing that we will consider is just simple fact, but these kind of simple things are accumulated. So before going in, I will show you how to handle sums or products. Mod 12. So this is the question, mod 12. So let's examine each number. 1, not very interesting, right? 1 is 1, right? 2 2, right? 3 factorial, 3 times 2 times 1, 6. Not very interesting. 4 factorial. 4 factorial equals 4, 3, 2, 1, 24. Congruent to what? If you divide by 12, the remainder is what? 0. Suddenly we get a very interesting number. 0 or 1 are very nice numbers in number theory. Right? 0 and 1 are very nice numbers, right? So we get this. Then what will happen? 5 factorial. 5 factorial equals 4 factorial multiplied by 5. Do you follow me? 5 factorial by definition is 4 factorial multiplied by 5. But 4 factorial is congruent to what? 0, right? So it is 0. Do you get it? 4 factorial is congruent to 0. So any following terms would become 0 in this calculation because of this fact. So any following terms, right, will be 0, right? For instance, here 100 factorial was given. In other words, any term after 4 factorial is meaningless, right? Any term after 4 factorial is meaningless. So what is your answer to the question? Oh, initially it looked very complicated, but after going through these steps, I found that only non-zero numbers that we need to consider are just these numbers, right? Just these numbers, because after, or even right at 4 factorial 0, right? 0. So because of this reason, I can rewrite the problem. 1 plus 2 plus 6 plus 0 plus 0 plus 0, or 9, right? So it is congruent to 9.
So if there was, if we were using, let's say, mod 11 or mod 13, a number that was prime, that wouldn't have that same.
Then around about 13 factorial, and then afterwards we will get zeros.
It would be 0.
Yes. Then, instead of just covering numbers and then examples, let's handle a little bit tougher thing. One direction is, the other direction is not easy. So assume that we have A is congruent to B. Then we have CA is congruent to CB. Is it true or not with mod N? Is this true or not? By property number 5, right? By item number 5 on the theorem having many properties, this is true. But we are not interested in this direction. Do you know what I mean? Usually, one direction is easy, the other direction is not easy. The other direction can be very helpful. So, I will prove the other direction. But first of all, this direction is correct, right? The other direction is not even correct. The other direction is not even correct. For instance, pick any number that is nice enough. So pick any number to show you. It's not a setup, so you can pick any number. 7. So I will use mod 7, right? Mod 7. Then take a look. 1 is not congruent to 2, right? 1 is not congruent to 2. But 7 is congruent to 14. In other words, C is 7, right? C is 7, and 1 and 2 are multiplied, then 7 and 14 are congruent to mod 7. So this is true, but this is not true. Do you get it? In other words, the other direction is not even true. Then what can you salvage? I want to focus on the other direction. One direction is obvious. The other direction is not even true. Then what can you salvage, or how can you change the statement? So I will describe the situation in general setting. CA is congruent to CB mod N. But what I want to say is A is congruent to B. In what sense? In what sense? With the same mod, it's impossible. With the same mod, it's impossible. So we want to use specific mod. Mod is this one? N over GCD. N over GCD. GCD of what and what? Of course, N should be used, right? Because we are handling N, right? But N and what? The only other number is C. A and B are arbitrary, right? But the only other number are C. So N over GCD, this we can salvage. So this is the fact. So when C times A is congruent to C times B, then something that we can salvage is A is congruent to B, not with the same mod, but N over GCD. Then let's go back and then check it. But if you don't understand this statement itself, ask me. In other words, with the same mod, no chance. But with different mod, it might be possible. Then what can you salvage? This thing. This is non-trivial theorem, right? This is the non-trivial case. Others are very straightforward. This is non-trivial. Then let's do it. First of all, here A is 1, B is 2, right? And then C is 7, right? C is 7, right? 7 times 1. And then this is 7 times 2. Do you get it? Then what is GCD? GCD of what and what? This N, and then this is C, right? This is C. So what is it? G is what? 7. Then what can you say? Mod this 7 over this GCD, mod 1. Mod 1, then with mod 1, all integers are congruent, right? Because if you subtract and then divide, then you will get remain the 0. Do you get it or not? So this is the one that you can salvage. So you should always see the easy direction and hard direction. When I asked the Goldbach conjecture, many people wrote down the reverse direction. Oh, Goldbach conjecture said prime number plus prime number 1 plus prime number 2 is even. Of course, odd plus odd is even. It's not the conjecture. It's true. Right? When you add two odd primes, it's even. It's not the conjecture. The conjecture is the reverse. If an even number is given, then we can find two numbers, P1 and P2. This is the conjecture. Do you get it? The other direction is too trivial. If we add just two prime numbers, odd prime numbers, then it's even, right? Obvious. So this is not the conjecture. Conjecture is for any even number, we can get two prime numbers, especially odd prime numbers, to get even. So you should always know easy direction and hard direction. And as I mentioned before, let's go back. This direction is very easy. A is congruent to B becomes C, A, C, B. This direction is easy. The other direction is not easy and not even possible in general. But if we salvage, then we can get this kind of state. Right? Mod 1. Not mod 7, mod 1. In any case, I mentioned it. Then with these things, I will state a few more cases. And then later, when you have enough time, we will return back and prove. So obvious corollary to this thing is if CA is congruent to CB mod n, so mod n, then, and GCD of n and C is 1, then A is congruent to B mod n. Why? Because n over GCD, GCD is 1. So n over GCD is 1. N over GCD is n, right? N over GCD 1 equals n. So we get this thing. And then corollary 2, if CA and then CB with mod prime, mod P, which is prime, right? Which is prime. Because it's prime and P does not divide C, then A is congruent to B mod n. Why? If prime does not divide the given number, if the prime does not divide the given number C, then GCD of prime and the C should be 1, right? Because it doesn't divide. Do you get it? Because P does not divide C, GCD of P and C should be 1 because it's prime. So n over 1. So it is 1. So all these are obvious things from GCD equal to 1 fact. So these are the things. Then oh yeah, yes, sorry, you are right. N is the mod thing, you are right, P. Thank you. And let's use example 4.4. And it says, consider this thing, 33 mod 9. And we find the common factor, 3 times 11, right? And then 3 times 5. Then what can we salvage from these things? Mod what? 9 over GCD, right? 9 over GCD. 9 over GCD. And GCD between two numbers, right? C and 9, right? So what is it? What is G? This GCD is what? GCD is 3, right? Why? Because 3 and 9, right? 3 and 9, and then it is 3. So we get mod 3. 11 and 5 are congruent with mod 3. Now I will briefly introduce the next very, very important concept for the remaining 15 minutes. And then later, whenever you have questions or difficulties, you can ask. But for the remaining 15 minutes, I will cover very, very important thing. Positional number system. In the past, people didn't use positional number system. In the past, many people didn't use positional number system. For instance, assume that you need to get your payment. Would you get this payment or the other payment? What payment would you get? This payment, right? Why? It's positional number system. In the past, people didn't use positional number system, and then they just say, oh, this is the number, right? 3, 4, and so, right? No big difference between this mark and this mark, right? No big difference. But now we are using positional number system, and it has meaning. What does this mean? In mathematical form, it has this meaning. 6 to the power of 6 times 10 to the power of 0, right? And then 5 times 10 to the power of 1. And so on, right? And so on. And then 1 times 10 to the power of 5. This is the meaning. Even though we just wrote down 1, 2, 3, 4, 5, 6, it has meaning like this. Or the other one, 6 times 10 to the power of 5, and then 1 times 10 to the power of 0. So this is the meaning. And because we used this 10 called base, right? 10 is base. We call this decimal system. So for a long time, people felt this could be the best. In some civilization, people use different base, like 12 or 60. So there were some different base. But 10 was regarded as the best one for a long time. But after computer era, people realized that there could be better system or something that is necessary. And the other two famous cases are binary and almost identical, but more convenient is hexadecimal system. And binary has base 2, hexadecimal has base 16. If you want the details of these things, you may take the course called Scientific Computation, and you may ask me to send you the summary about these kind of things, but I will cover essential part, not very general thing that can be covered in scientific computation course. So base 2 means there are only 2 numbers that you can use. In other words, I can say x to represent 0, and then x to represent 1, or anything. And I will mention about the reason why this is so important. Hexadecimal, you can use 16 different letters, right? 16 different letters. Anything that you can create, and then you can distinguish, you can use 16 letters. But why bother? If you use these things, we don't recognize what it means. So people decide to use our number system. In other words, 0 and 1, right? 2 numbers can be used to represent any number. So 0 and 1 are used. And here, instead of using these things, people used 0, 1, 2, and then up to 9. Total 10 numbers, right? 0 up to 9, 10 numbers. But we need 16 numbers. So people tried other things, but they decide to use alphabet. A is 10. A represents 10. B represents 11. And C represents 12. I don't count, so you just track them. F represents 15, right? So total 16 numbers. So for instance, in binary system, 101 represents 1 number in positional number system, and in hexadecimal system, FF represents 1 number. So my quick question is, actual decimal number represented by binary number. So if we have this kind of binom number, what is the number in decimal system? This is equal to what? 5. And this is equal to what? 255. How do I know it? I memorized it. So I will show you. By positional number system definition, when we have this kind of representation, we use 10 to the power of 0 with the last number, right? And then base to the power of 1 with the next number, and so on, right? So base to the power of 0, base to the power of 1, and so on are used. So I should translate this number. 101 equals the last number 1 multiplied by base what? Base is 2. 2 to the power of 0. And then 0 times 2 to the power of 1. And then 1 times 2 to the power of 2. Then, what is it? 4, 0, 1, 5. Right. I can memory up to this point, right? What about 50 to 55? Let's do it. F means 15, right? In decimal represent 15. And then 16 to the power of 0. Do you get it? And then next F, 15 multiplied by 16 to the power of 1. Then 16 is the common, 15 is the common factor. 15 is the common factor. Then 16 here, and then 1 here. So 17 and 15 multiplied, right? Because I do not allow calculators, I will use this thing. So 5 times 1 is 5. And then 5 times 7 is, what is it? 35, right? 1 times 7 is 7. 1 times 1 is 1. Then as you can see, this addition gives us 5. This addition gives us 5, right? And then 1 carried over 2, right? So it is 255. So these are the things that we can consider. Then generally we can convert the numbers. So decimal number is the one that we can recognize. And then binary number is used in computer. And almost identical conversion is hexadecimal, right? Hexadecimal. So let's write the number 0, 0, 0, 1, 1, 1, and then 2. Do we have 2 in binary system? We don't have 2. When you convert it in decimal, then you have 2. But in binary system, we have 1, 0, and 1. So we should carry over the 1, 0. Do you get it? So 1, 0 is not 10. In binary system, it means 2. In hexadecimal system, it is 2. It is almost identical, so I will not even write down anything further. And then 3, then what should we do? 1, 1, right? Do you get it? Or not? It is 2 plus 1. 2 plus 1. This represents 1 times 2 to the power of 1, and then 1 times. So I will write it. This represents 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. Do you get it? Same way, this represents 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. Do you get it? I will be slow here, so if you don't get it, ask me. Then 4. How can you do it? We used up all possible numbers, so it is 1, 0, 0. It means 1 times 2 to the power of 2, 0, 2 to the power of 1, 0, 2 to the power of 0. Right? So instead of writing down all these things, we just extract. We have extracted this and this one, this and this one, this. So we just extract these things to represent this number. Do you get it?
So 8 would be 1,000?
Right, right. So
you can look at the decimal and see what the largest square of 2 or the largest power of 2 is.
right, right. So we can write it this way. 16 is this one. If you don't understand, you can stop me.
Now the hexadecimal will be different above 15, though. That's when we
Right.
the letters.
Right. If you don't understand, you can stop me anytime. I will use these commas. So we can write this kind of way. And we can add these things and then do all sorts of things. But this is not our major concern. Oh, we don't have enough time. So I will just write down as many numbers as possible. But if you completely understand, you may leave the room.
So we're already concerned with hexadecimal.
The text didn't cover, so I don't cover. But if it's a computer science course, then I would take. But there is a straightforward conversion between these things and hexadecimal numbers. For instance, 4 digits creates one hexadecimal number.
You can block things.
Right, right. 4, 4, 4. So assume that you have this thing, then you should represent this thing. That means 3, right? So it is 3, and then this portion becomes O in hexadecimal, and then you have 0, and then this is 8, right? So 8, 0. Sorry. This is not 3, it is 2, right? I was confused. So this is 2, 0, right? This is 4, 0, right? And then 4, and then 4, then this gives 8, 0, right? And then this gives us 4, right? This block of 4 becomes 0, right? And then 1. So there is straightforward conversion between binary and hexadecimal. So once you learn by binary, then the conversion is very straightforward because we can just block by taking 4 digits. And I will tell you the reason later. But right now, we focus on decimal to binary. And next time, we will use this